Industrial safety is not a collection of annoying rules invented to slow production. It is an engineering, management, and public health response to real failure modes. The question is not whether work involves risk. The question is whether we identify that risk before people pay for it. To understand how the United States developed modern workplace safety, start with what work looked like before protection was expected. During the 19th century, industrialization transformed American work. Steam power, textile machinery, railroads, mining, and mass production increased output dramatically. They also concentrated people around moving belts, exposed shafts, hot surfaces, toxic materials, unstable excavations, and crowded buildings. Many machines were built to produce efficiently, not to fail safely. If a sleeve caught in a rotating shaft, the shaft did not stop. If dust accumulated inside a building, production might continue until an explosion revealed the problem. If a worker developed lung disease years later, connecting the illness to the job could be difficult. Children, immigrants, and people with limited economic choices often perform some of the most dangerous work. Safety rules varied widely. Effective inspection was inconsistent, and when someone was injured, the burden commonly landed on the worker and the worker's family. The technology was advancing faster than the systems needed to control its risks. Early workplace hazards were not simply a knowledge problem. They were also an incentive problem. When production benefited an employer but the consequences of an injury fell mainly on a worker, the financial pressure to prevent harm could be weak. Workers, labor organizations, physicians, reformers, insurers, and some employers began pushing for change. Factory inspection expanded in some states. Safety campaigns emerged. A major shift came when states adopted workers' compensation systems, which made workplace injuries a more direct organizational cost. Wisconsin established an effective state workers' compensation program in 1911, and other states followed. Compensation did not make dangerous equipment safe, but it changed the economic calculation. An injury was no longer only a private family tragedy. It became a measurable cost of doing business. That distinction still matters. Good safety programs do not depend exclusively on good intentions. They connect human consequences, operational reliability, legal responsibility, and management accountability. Mining exposed the weakness of early industrial safety with brutal clarity. Underground work combined confined spaces, limited escape routes, explosive gases, combustible dust, and ignition sources. Those conditions could turn one initiating event into a disaster affecting an entire workforce. In December 1907, an explosion at the Monongah coal mines in West Virginia killed 362 people, according to the Mine Safety and Health Administration. It remains the deadliest mining disaster in United States history. The engineering lesson is larger than the specific mine. A dangerous system can appear productive until several conditions align: fuel, oxygen, ignition, confinement, and people who cannot escape. Managing only one visible symptom is not enough. You need ventilation, monitoring, equipment controls, inspection, emergency planning, and a way for workers to report dangerous conditions. Disasters like Monongah helped drive federal attention to mine safety and the creation of the Bureau of Mines. But another catastrophe would bring the same question into the center of an American city. On March 25, 1911, a fire broke out at the Triangle Shirtwaist Factory in New York City. The people inside were largely young garment workers, many of them immigrants. 146 workers died. The tragedy exposed a familiar chain of failures: combustible materials, crowded conditions, inadequate escape routes, and exits that workers could not use effectively. Firefighting equipment could not solve a situation in which people were already trapped. Public outrage helped drive investigations and stronger state factory laws. Reformers examined building conditions, fire prevention, exits, sanitation, and the actual working environment, rather than assuming the market would correct the problem by itself. Frances Perkins, who later became the United States Secretary of Labor, was among the figures profoundly affected by the fire and the reform movement that followed. For an engineering student, the principle is straightforward. Emergency egress is not optional hardware. It is a life safety function. An exit that does not work under emergency conditions is not an exit. Some workplace hazards announce themselves immediately. Others do their damage gradually. A crushed hand is obvious. Damage from lead, asbestos, silica, solvent vapor, noise, or repetitive strain may develop over months or years. This creates a different engineering problem. You cannot reliably judge a toxic exposure by whether it looks dramatic, smells strong, or causes immediate pain. Exposure depends on concentration, duration, route into the body, and the properties of the substance. Some damage can be permanent before a worker realizes anything is wrong. The distinction between safety and health matters. Safety often addresses immediate injury, falls, fire, electrical contact, or moving machinery. Occupational health also addresses long-term exposure, respiratory disease, hearing loss, chemical toxicity, and other conditions connected to work. A complete safety program, therefore, includes more than guards and hard hats. It includes monitoring, ventilation, substitution, exposure limits, training, medical surveillance where required, and investigating what workers are actually exposed to. Physician Alice Hamilton helped change how Americans understood workplace disease. Working with immigrant and industrial communities in the early 20th century, she investigated the connections between working conditions and illnesses caused by hazardous substances. Rather than treating each sick worker as an isolated case, Hamilton asked what people handled, what they breathed, where the material came from, and which industrial processes were responsible. Her work helped establish occupational medicine and industrial hygiene as evidence-based fields. That approach should sound familiar to anyone studying engineering or troubleshooting. Observe the failure, identify the exposure pathway, collect evidence, locate the source, then change the system. The point is not to wait until an entire workforce becomes sick and then argue about whether the pattern is a coincidence. The point is to investigate early enough to prevent additional harm. Modern air sampling, exposure assessment, ventilation design, and chemical hazard communication all build on that logic. During construction of the Hawks Nest Tunnel in West Virginia in the early 1930s, workers encountered silica-bearing rock. Drilling generated respirable crystalline silica, particles small enough to enter deep into the lungs. Many workers developed silicosis, a serious and irreversible lung disease. The exact death toll is disputed. NIOSH notes that historical estimates vary widely, so a precise number should not be presented as settled fact. What is not disputed is the underlying hazard. Breathing concentrated silica dust can permanently injure or kill workers. The controls are not mysterious. Use wet methods or effective dust extraction. Enclose or isolate the process. Measure exposure. Maintain equipment. Provide appropriate respiratory protection when required. Train workers to recognize the hazard. Silica is not just mining history. It remains relevant when cutting concrete, stone, masonry, or engineered materials today. OSHA issued updated respirable crystalline silica standards in 2016. A hazard does not disappear just because it has been known for generations. By the middle of the 20th century, workplace safety had improved in some industries and some states. Workers' compensation, building codes, factory inspection, professional safety organizations, labor advocacy, and employer safety programs had all contributed. But protection remained uneven. Industrial processes were becoming more complex. Chemicals, construction equipment, powered machinery, and large production systems introduced hazards that did not stop at a state line. Occupational disease could be difficult to detect, and employers operated under inconsistent standards. The growing argument for federal action was not that no safety efforts existed. It was that a patchwork of protections left too many gaps. The United States needed a more consistent baseline, an enforcement mechanism, research into emerging hazards, and better worker access to information. That distinction is important. Modern workplace safety did not begin on a single day. It developed through decades of pressure, investigation, engineering, state reforms, and preventable tragedies. Federal legislation assembled those efforts into a broader national framework. President Richard Nixon signed the Occupational Safety and Health Act on December 29, 1970. The Occupational Safety and Health Administration opened on April 28, 1971. The law established a broad national commitment to safe and healthful working conditions. OSHA develops and enforces workplace standards, conducts inspections, provides education and compliance assistance, and works with approved state plans. The National Institute for Occupational Safety and Health, or NIOSH, conducts research and develops recommendations for preventing work-related injuries and illnesses. Think of the distinction this way. OSHA is primarily the standards and enforcement side. NIOSH is primarily the research and recommendations side. State agencies may operate approved occupational safety programs, but they must meet federal requirements. The Act also created an important general expectation. Employers are responsible for maintaining a workplace free of recognized serious hazards. That does not mean every possible danger can be eliminated. It means foreseeable hazards cannot simply be dismissed as part of the job. A safety standard is not effective because it exists in a binder. It works when it changes the physical workplace and the way work is performed. For a machine hazard, that may mean a fixed guard, an interlocked door, or a verified safe operating distance. For a chemical hazard, it may mean a labeled container, a safety data sheet, ventilation, exposure monitoring, and training. For an emergency, it means clear exits, alarms, a response plan, and employees who know what to do. The details depend on the hazard, but the structure is consistent. Identify the risk. Select an appropriate control. Train the people involved. Verify that the control actually functions. Maintain it over time. Correct problems when conditions change. That is why a safety program includes equipment, written procedures, inspection records, reporting, and management responsibility. Paperwork is not the objective. Evidence that the hazard has actually been controlled is the objective. You cannot protect yourself from a chemical hazard if nobody tells you what the chemical is. OSHA's Hazard Communication Standard, established in 1983, created a structured approach for communicating the hazards associated with workplace chemicals. Employees need access to meaningful information, product identification, hazard warnings, safe handling procedures, emergency measures, and safety data sheets. Containers must be properly labeled. Training must explain the hazards present in the actual workplace. In 2012, OSHA updated the standard to align with the globally harmonized system, helping standardize hazard pictograms, classifications, labels, and safety data sheets. This matters in a machining lab, welding area, automotive shop, maintenance department, or additive manufacturing facility. Coolants, solvents, resins, adhesives, compressed gases, and metal powders do not become harmless because they are familiar. A missing label is not a minor housekeeping issue. It removes the information needed to choose ventilation, gloves, eye protection, spill response, and emergency treatment. Suppose a conveyor jams and a technician reaches inside to clear it. The machine is stopped, so the task looks safe. But what happens if someone restarts it? What if a hydraulic cylinder moves, a spring releases, or a raised component falls? Stopped is not the same as isolated. OSHA issued its Hazardous Energy Control Standard, commonly called Lockout-Tagout, in 1989. The standard addresses servicing and maintenance when unexpected startup or release of stored energy could injure workers. Depending on the equipment, controlling energy may involve electrical disconnects, hydraulic pressure, compressed air, gravity, springs, or other stored forces. The basic idea is to isolate the energy source, apply the required lock or tag, dissipate or restrain stored energy, and verify the equipment is in a safe state before work begins. The verification step matters. A red button, a touchscreen command, or a machine that happens to be quiet is not proof that hazardous energy has been controlled. Some failures injure one person. Others can damage an entire facility. Process safety focuses on high-consequence events involving hazardous chemicals, stored energy, fires, explosions, or major releases. OSHA issued its Process Safety Management Standard in 1992, following catastrophic chemical incidents. The standard emphasizes identifying hazards, understanding equipment and chemicals, maintaining mechanical integrity, training operators, investigating incidents, and controlling changes. Consider a simple equipment replacement. A hose, valve, or fitting may physically connect to a system while still being wrong for its pressure, temperature, or chemical exposure. If the change is not evaluated, normal production can gradually move a facility toward a failure nobody intended. Process safety asks questions beyond whether a worker remembered safety glasses. What can fail? What happens if it fails? What barriers prevent escalation? How do we know those barriers are still working? Production reliability and safety are not separate conversations. Poorly understood equipment, deferred maintenance, undocumented modifications, and unclear operating limits threaten both. On September 3, 1991, a fire tore through the Imperial Food Products poultry processing plant in Hamlet, North Carolina. A ruptured hydraulic line released oil near a natural gas-fired cooker. The oil ignited. Of roughly 90 employees working that shift, 25 were killed and 54 were injured. OSHA documented locked or obstructed exits, inadequate exit markings, excessive travel distances, missing alarms, and failures in emergency planning. Stop and compare that with the Triangle Shirtwaist Fire. Different industry, different state. 80 years later, the same essential failure. Workers could not get out. By 1991, OSHA existed. Fire safety requirements existed. Exit requirements existed. Their presence on paper did not protect people when the workplace itself was allowed to remain unsafe. For North Carolina students, Hamlet is not distant industrial history. It is evidence that prevention depends on implementation, inspection, maintenance, accountability, and the willingness to act when an obvious hazard is normalized. Sugar does not look like an industrial explosive. Neither does flour, wood dust, or a pile of fine metal powder. But when combustible material is finely divided and suspended in air, it can burn extremely rapidly under the right conditions. On February 7, 2008, an explosion and fire at the Imperial Sugar Refinery near Savannah, Georgia, killed 14 workers and injured 38, according to the Chemical Safety Board. Investigators identified major accumulations of combustible sugar dust and problems involving equipment design, maintenance, and housekeeping. The technical lesson is that a material's hazard can change when its physical form changes. Aluminum in a solid block and aluminum suspended as fine powder are not the same exposure or fire scenario. Controlling combustible dust requires more than telling workers to clean up. It requires suitable equipment, dust collection, process containment, safe cleaning methods, ignition source control, inspection, and recognition that secondary explosions can spread an initial event. Modern occupational safety uses a practical framework called the hierarchy of controls. It ranks protection strategies by their general effectiveness. First, eliminate the hazard. If a dangerous operation is unnecessary, remove it. Second, substitute a safer material, process, or piece of equipment. Third, use engineering controls. Guards, interlocks, ventilation, barriers, enclosure, automation, or redesign tools. Fourth, apply administrative controls, procedures, scheduling, restricted access, training, and exposure limits. Fifth, use personal protective equipment such as safety glasses, gloves, respirators, hearing protection, or fall arrest equipment. PPE matters, but it is generally the last line of defense because it depends on correct selection, fit, condition, and consistent use. A well-designed guard or enclosure protects people without requiring them to remember a perfect response every second. The hierarchy is not an argument against training or protective equipment. It is a reminder to ask the more useful engineering question first. Can we remove or control the hazard before it reaches the person? Automation can reduce exposure to repetitive, heavy, hot, or hazardous work, but it also introduces new failure modes, unexpected motion, crushing between a robot and a fixture, stored pneumatic energy, changing work envelopes, and control system faults. OSHA notes that many robot incidents occurred during non-routine conditions, such as programming, maintenance, testing, setup, and adjustment. That makes sense. Normal production may happen behind a barrier. Troubleshooting often puts a person closer to the hazard. A safe robotic installation uses risk assessment, appropriate safeguarding, interlocked access, properly designed control systems, verified energy isolation when required, and clear procedures for entering the cell. Collaborative operation is not automatically safe simply because a robot is marketed as collaborative. The entire application, including tooling, speed, force, workpiece, and surroundings, must be evaluated. The modern version of an exposed 19th century line shaft might be a sophisticated automated system that nobody expects to move. The technology changed. The need to control hazardous motion did not. Additive manufacturing is often presented as clean, digital, and futuristic. The file may be digital. The hazards are still physical. NIOSH identifies potential risks, including inhalation of powdered materials or emissions, skin exposure to resins and solvents, fire or explosion involving combustible substances, and mechanical or ergonomic injuries during machine support and material handling. Depending on the process, high-powered lasers and other energy sources also require control. For metal powder bed fusion, the highest exposure may occur during powder loading, part removal, depowdering, cleanup, filter changes, or waste handling rather than while the machine is printing. Fine aluminum or titanium powder can create inhalation and combustible dust concerns. Inert gas systems can also introduce atmosphere-related hazards that require proper assessment. Apply the same hierarchy: closed material transfer, suitable ventilation, controlled housekeeping, correct equipment and procedures, training, and task-appropriate PPE. New technology does not suspend old physics. It creates a new situation in which those principles must be applied. Historical progress is real, but the problem is not finished. The latest complete federal figures available for this production cover 2024. The Bureau of Labor Statistics recorded 5,070 fatal occupational injuries in the United States that year. That equals a fatal injury rate of 3.3 deaths per 100,000 full-time equivalent workers. On average, one worker died from a job-related injury every 104 minutes. Private industry employers also reported approximately 2.5 million non-fatal workplace injuries and illnesses in 2024. The reported case rate was 2.3 per 100 full-time equivalent workers. Those figures describe different measurements and should not be combined as though they came from the same population or captured every occupational illness. They do, however, make the central point clear. Workplace safety is not a historical issue solved in 1971. It remains an active design, management, training, and public health problem today. When you enter the workforce, you are not supposed to guess your way through a dangerous job. OSHA states that workers have the right to safety and health training in a language they understand, access to relevant hazard information, safe equipment, and required protective equipment. Workers can report hazards, injuries, or illnesses, request an OSHA inspection, and raise safety concerns without unlawful retaliation. If a supervisor responds to a legitimate safety report by threatening, punishing, or firing someone, that may involve whistleblower protections with specific filing deadlines. Refusing dangerous work can also be protected under certain circumstances, but the legal conditions matter. It is not an unlimited right to leave any task whenever it feels uncomfortable. When a serious hazard exists, report it promptly, follow established procedures, and contact OSHA or the appropriate state plan agency when necessary. The practical message is simple. Ask what the hazard is, ask how it is controlled, and speak up when the control is missing or not working. The history of industrial safety is not a straight line from ignorance to perfection. It is a record of hazards recognized, protections developed, lessons forgotten, and lessons learned again. Monongah showed what happens when explosive conditions and limited escape align. Triangle and Hamlet showed that workers still die when exits fail, even across different generations. Hawk's Nest showed the cost of invisible exposure. Modern robotics, chemical systems, and additive manufacturing show that new technology creates new combinations of familiar risks. Whether you become a machinist, maintenance technician, welder, designer, engineer, healthcare worker, or supervisor, you will make decisions that affect someone's exposure to danger. Ask 5 questions. What is the hazard? Who can be exposed? What controls it? How do we know the control works? And who has the authority to stop the job when something is wrong? Safety is not a poster on the wall. It is a system built into equipment, processes, decisions, and workplace culture. The purpose is simple. Do the work and make sure everybody gets home.